Okay, welcome back. This section is on logarithmic functions. Logarithmic functions are the inverses of exponential functions. They're very useful to get variables out of the exponent of an exponential function. We'll talk a little bit more about that, but the first thing we want to do is show the relationship between an exponential function and a logarithmic function. So we've seen functions like y equals a to the x, right? Some function, y is the function f of x, but I'm just going to write it as y because we're going to switch stuff around a little bit, and it's easier to use this y notation for now. So y equals a to the x. This is my exponential function. And the logarithmic function that pulls this x out of the exponent is this. It would be the log. We would write log for logarithm, base a of y equals x. This is the equivalent logarithmic expression. These two are equivalent. And we show equivalence by a double arrow. Right? This is the same thing as this, if I were to write these things together. Right? This here, though, is my logarithmic equation. My exponential equation on the left, log equation on the right, they are equivalent equations. Right? So we'll talk about how to write a few of these as logarithms, or we'll show a few examples, and then we'll come back and talk about what the log is really and how to play with it a little bit more. I might have a true statement like, say, 3 to the 4th is 81. Right? Now, we saw, maybe I shouldn't have erased it, but I had y equals a to the x became the log base a of y equals x, right? The a was the base of the exponent, but it's also then going to be the base of the logarithm, and we write the base of the logarithm as a subscript, a lower down value, so it's the log base a of y equals x, right? Now you notice that the a is with the x on one side of the equation of the exponential, but the a kind of comes over and becomes the base of the log of the other side. So here, my a is on the left-hand side, it's my 3. My 3 is the base, and so my 3 is going to jump over to the other side, and it'll leave me with this 4. So this is equivalent to 4 being left alone. The 3 jumps off to the other side, becomes the log base 3 of that 81. Right? And you can, of course, write it the other way. You can write this as log base 3 of 81 is equal to 4. Right? Either way. Let's see a few more of these. 2 to the 5th is 32. So if I want to write this as a logarithmic expression, this becomes the log base 2, right? 2 becomes the base, and really it should jump over to be with the 32. So since I wrote it here, it matches up with the 32, and it doesn't matter if you move the 2 over to meet with the 32 or you just switch the 5 in the 32's place. But this is my logarithmic expression, right? I can think of it that way, or I can think of it as simply the 5 drops down, the 2 jumps over to become the base of the log base 2 of 32. I don't know what's going on with that 2, but these are the same thing, they're just on the opposite sides, right? The important thing is that the base of the exponent hooks up as the base of the log of the other side. So if we have just random log base a of x equals w, right? I can rewrite this as an exponential simply by, well, let's back up. Not quite there yet, sorry. If I have maybe, say, a to the w equals x, right? I can rewrite this as a log by, the a is the base, so this becomes log base a, and then the a needs to hook up with the x, so it's log base a of x equals w, right? And what I tried to do before is go backwards with this, which we'll want to do. If a is the base of the log, and I want to rewrite this as an exponential, I just go backwards. And this a becomes the base of the exponential, hooked up with the other side, which is a w, and is equal to the other guy, x, and I'm back to what I started with, right? So we can undo these as well. So let's see a few more of these. If I have, say, log base 2 of 16 is 4, right? To rewrite this as an exponential, again, I would take that base, raise it to the other side, and equal to 16. So that is to say, 2 to the 4th is 16, which is true, right? 2 to the 4th is indeed 16. And these are equivalent. Alrighty. If I have, say, log base x of y equals z, to rewrite this as an exponential, that is x to the z equals y. And again, those are equivalent statements. Good. Now, we will be asked to graph some of these, and it may be difficult to graph an exponential, it may be difficult to graph a logarithm, but we saw graphing exponentials, and there's that relationship between the logarithm and exponential that we can exploit to make graphing a logarithm easier. So let's say that we are asked to graph y equals the log, let's say base 2 of x. Okay. If I came through and said, well, here's an x chart and a y chart, and I want to plug in values of x to figure out y, it's hard to do that, especially since I don't know really how to evaluate log base 2 of anything just yet, right? So what I want to do is note that this is the same thing as 2 raised to the y equals x, and it looks like now x is a function of y. So I can exploit that and say, hey, I can plug in values of y, say -2, -1, 0, 1, and 2, into this exponential equation and figure out their x values, right? So if y is -2, that is x equals 2 to the -2, which is 1 over 2 squared, which is 1 over 4. If if y is -1, then x is 2 to the -1, which is just 1 over 2. If y is 0, x is 2 to the 0, that should be easy, that's 1. But we saw this exponential relation. 1/4 multiplied by 2 is 1/2, which multiplied by 2 is 1, which multiplied by 2 will give me 2, which makes sense because if y is 1, 2 to the 1 is 2. If y is 2, 2 squared is 4, but again, we're just multiplying by 2 here. And we see that exponential relationship again appear, but now that exponential relationship is in the is in the x value, right? So I have a bunch of points and I can plot this. Let me clear up a little room to do that. Alright, first I have x is 1/4, so I'll put maybe 1 right here, 2 right there. But if x is 1/4, I'm just 1/4 of the way to 1, but y is -2, so 1, 2, maybe right there. If x is 1/2, so halfway to 1, y is -1. If x is 1, y is 0, so I go through there. If x is 2, y is 1. If x is 4, y is 2, so I keep going a little bit more, 3, 4, to get to there. And you can see if I keep going, say y is 3. If y is 3, then I would get 2 to the 3, which is 2, 4, 8, right? So it's my x values that kind of rocket off to the right as my y values increase. So by the time I'm at 3 in my y, I'm all the way over there, way off the screen for my x value. Right? And again, we saw in exponentials how we asymptotically approached a line, and we're going to do that same thing here, because I'll never get x to be 0, and I'll never get x to be a negative, but I can get close, and it's going to get closer and closer. So there is this asymptote we see here, and I come off of it, and simply have an exponential throw off to the right. And this is our typical logarithmic graph. This is a log base 2. Most of the time you'll see these points, unless it's been shifted, you'll see this point, 1, 0. And then your base, whatever that is, right? In this case it's 2, which is why I go through the point 2, 1. If my base were 3, I would go through the point 3, 1. If my base were 10, I would go through 10, 1, right? Because that would be y is your power here, and it's the first power of whatever your base is. So 1 for the y, and whatever your base is for the x. Okay. And that's the graph of log base 2 of x. All right, let's see another one. Let's say we want to graph y equals log base, let's go log base 7 of x. Right? So we would start off by noting that I can rewrite this as 7 to the y equals x. And so when I create my xy chart, I'm going to treat x as a function of y, and I'll throw in some y values here. Those same ones, say -2, -1, 0, 1, and 2. They're a good place to start typically. If y is -2, then x is 7 to the -2, which is to say 1 over 7 squared, or 1 over 49, right? If y is -1, then x is 7 to the -1, which is just 1 over 7. And again, we see this exponential increase in my x. So multiply this by 7 gives me 1, multiplied by 7 gives me 7, and then 49. But I'm so far to the right here with my x that it doesn't really matter, right? And again, if I keep going negative values of y, -3 is just going to give me 1 over 7 to the 3rd, which is still not negative, but it's closer and closer to 0. So I can graph this. So I have some points. X is 1 over 49, so very close to 0, when y is -2, so we'll just say it's maybe there. X is 1 over 7, so really not a whole lot further away, but here, let's call it, and -1, so maybe there. And I have this point again, 1, 0. That should appear quite often, unless I've shifted up, down, left, or right. 7, 1, right? So it's that base value of 7 and 1. So all the way here before I hit 1. And then by the time I hit y is 2, I'm way off there. So you can see that having a larger base means that I have a much sharper turn. And I rocket off quite a bit faster in the x direction. There's that graph. Let's take a look at another one of these. Let's now look at the log, say, base 1/3 of x. See what happens when my base is a fraction that's less than 1. Right? Well, again, I can rewrite this as the base 1/3 to the y is equal to x. So again, I'll find some x, y values. I'm treating x as a function of y, so I'm going to plug in, say, -2, -1, 0, 1, and 2 in for y, and figure out my associated x value. But if y is -2, then I have x is equal to 1/3 to the -2. But that's the same as 3 to the 2, and that is 9. If y is -1, x is 1/3 to the -1, but that's the same as 3 to the 1, which is 3. Again, we can see that exponential pattern here. 9 multiplied by 1/3 is 3. I'm going to multiply that by 1/3 to get 1. 1/3, 1/9, right? If you do it out, it's all the same. X equals 1/3 to the 0, but that's just 1. X equals 1/3 to the 1, but that's just 1/3, and we see the pattern, of course, forming itself. So I want to graph these. And this graph will look just a little bit different. Okay. So I have x is 9 when y is -2. That's all the way over here. X is 3 when y is -1. So right here, covering up my 3 a little bit. X is 1 when y is 0. This is not a surprise. That 1, 0 is typically there. And my base was 1/3, so again I get that base when my y value is 1, but that base is 1/3, so it's maybe right here. When x is 1/9, so just barely off the 0, y is 2. And I can see that as I approach 0, I'm going up now. And then my sharp turn off to infinity, so it really is just kind of flip this guy on its head. I still have the asymptote up. I just come down here and do something like that. Right? So if I have a fraction as a base that's between 0 and 1, it really just kind of flips this guy upside down, and my logarithm is inverted, flipped about the x-axis. All right, good. So these graphs have all been fairly basic, meaning that there's no shifts in them, but we can see things that get shifted. For example, I might be asked to graph y equals log base 2 of x minus 3. So to rewrite this as an exponential, I would write this as 2 to the y equals, and what's inside the logarithm here is x minus 3, but if I want to treat x as a function of y, I want to get x completely isolated, so I'll add 3 to both sides. So that is to say I have 2 to the y plus 3 is equal to x. Right? Now x is a function of y, where y is the exponent over the 2, and then I simply add 3. So again, I'll find some x and y values. Throw in your typical -2, -1, 0, 1, 2, 3. Maybe not 3, I don't know, doesn't matter. My typical ones are there. And so if y is -2, x is 2 to the -2 plus 3. The 2 to the -2 is 1/4. So that's 3.25-ish, 3 1/4. If y is negative 1, that tells me that x equals 2 to the negative 1 plus 3, but that's 1 over 2 plus 3, or 3.5-ish. And it doesn't matter if you think of these as decimals or 3 1/4, 3 1/2, right? It doesn't matter. If y is 0, then I have x equals 2 to the 0 plus 3, but that is 1 plus 3, and that is 4. If y is 1, then I have x equals 2 to the 1 plus 3, but that is 2 plus 3, and that is 5. If y is 2, that gives me x equals 2 to the 2 plus 3, but that's 4 plus 3, and 7. So that should give us enough points that I can get a pretty good idea of where this is graphing. Let me get rid of all of this algebraic work here. To graph this, I have the point 3. Let me throw some tick marks on here. Alright. 3 1/4, so barely off of 3, and negative 2. Maybe there. 3 1/2 and negative 1, so maybe there. 4 and 0. 5 and 1. And then 7 and 2. And you can see as I get more and more negative values for y, if we ignore this 3 for a moment, the smaller and smaller y gets, the more negative it gets, the closer 2 to the y gets to 0, and therefore the closer the entire 2 to the y plus 3 gets to 0 plus 3, or 3. And so now I'm asymptotically approaching the line x equals 3. And so I asymptotically come off of that line and then make my shift to the right. Now we can see that that makes sense because in the parentheses where the x is, it's x minus 3. That's a shift opposite that sign, so it's a shift to the right by 3. And that's all we've really done here, is shifted log base 2 of x to the right by 3 units. All right, that'll do it for today. Thank you, and I'll see you next time.